In this video, we'll look at an example for view factor. So in this example, uh, we will see how to apply how to use the table for table 13.2 and how to use the equations given for view factor in finding the view factor for different scenarios. We'll also look at developing a network of resistances, your radiation surface resistance and your V factor resistances, and we'll find the net rate of heat transfer from a surface to another surface. So let's dive into the example. So in this example, we have a heater plate, which which is exposed to infrared radiation. The dimensions of this plate are given. The width is 1 meter and the area is 15 meters. And there's a solar absorber coating which sits over the plate, and it is 1 meter away from the heater plate, and it has a length of 10 meters. So the length of this collector plate is 10 meters, and the upper surface of the absorber and the lower surface of the heater are insulated. So this means that there is no heat transfer from the upper surface of the collector and the lower surface of the absorber. And what we need to find is we need to find out the net rate of heat transfer to the absorber surface. So how much heat is transferred to the absorber surface, which is surface 2 right here. So how much heat is transferred to this surface right here. Okay. So now we know that this particular setting is placed in a room. So that's why it's given that the room is at a temperature of 300 Kelvin, and its emissivity is given as 0, and we'll see why that is. And we know the surface temperature of surface T2. We know that surface temperature of the heater surface T1, it's 1000 Kelvin, and we know the areas and the emissivities as well. So to begin with this problem, what we do is, because we don't have an enclosed surface, we assume or we draw a imaginary surface or imaginary enclosure around the collector and heater assembly. So we draw this square dotted line, which makes an imaginary enclosure, and we'll name this imaginary surface as A2 prime and these two surfaces as A3 prime. So because the system is symmetric, even though we have A3 prime and A4 prime, due to symmetry, they will always be equal. So let's say they are A3 prime. Both these surfaces are A3 prime. Okay. So this is what we've done. We've taken an imaginary enclosure so that we can use the summation rules and the reciprocity rules to find the different view factors. So moving on to our assumptions, the assumption that we have is that the system is at steady state. We are neglecting the effect of convection. There will be air in the room, but we're ignoring the heat transfer due to convection in this case. We are assuming that the heater and the absorber surfaces are gray and diffuse, which means uh, gray surface means that your alpha will be equal to epsilon, so your absorptivity will be equal to emissivity, and diffuse means that these surfaces will radiate heat in all directions equally. So the uh, emission from the surfaces will not be directional, it will be equal in all directions. And our fourth assumption will be, because the surrounding room is large, it will behave as a black body, and we just saw the derivation of this assumption in our video related to view factors. So because if we have a larger area, the denominator gets large, and our resistance due to thermal surface becomes zero, and we can assume that that surface is a black body. So that's why. So that gives us the uh, the surface radiation resistance makes equal to zero. So because it's a black body, your emissivity is 1. So 1 minus epsilon will be equal to 0, and our resistance due to that will be 0. So our surface 3, there's no surface resistance offered by it. So our RT radiation by surface 3 is 0. That is due to assumption 4. So let's find out, or let's calculate the values that we know. So let's begin with calculating the radiosity by surface 3. Because our resistance is 0, the radiosity will be equal to the emissivity, or the emissive power, which is nothing but sigma times T3 to the power 4. Now why will this be equal? So if you remember that our potential, so the potential across our surface resistance was J3 and EB3. So this was our driving potential. But if our resistance goes to 0, this means that our entire body is at an equal potential, which means that J3 is equal to EB3. So that's why J3 is equal to EB3. It's nothing but sigma T3 to the power 4, which and plugging the value of sigma and T3 gives us 459 watt per meter square. The next thing that we can calculate is the ms, how much here flux is emitted by surface 1. So we know the temperature, we know the value of sigma. Plugging in these values, uh, we get EB1 as 56,700 watt per meter square. Okay, so we have J3, we have EB1. Now let's move on to the view factors, and let's list down what all we know. So we know that view factor of 1 1 will be equal to 0, because surface 1 cannot view itself, and view factor for plane and convex surfaces, uh, view factor of viewing themselves is 0. So that's why we can write down f11 equal to 0. By reciprocity, the relation that we know is that uh, A2 F23, that's this right here, will be equal to, as in the view factor of 2 viewing 3, and 3 being the entire room, is equal to uh, your 2 viewing just this dashed line, which is represented by A3 dash. So whatever radiation leaves surface 2 and is intercepted by the room, which is our third surface, will pass through this dashed line A3. Okay, that's why we can make this assumption, which is A2 F23 equals to A prime, and should be A2 prime F2 prime 3. Okay, so whatever radiation is emitted is intercepted by the dashed line A2 prime as well. Okay, so that's why we can write this relation right here. From symmetry, we can say that f2 prime 3, that's f2 prime 3, will be equal to f1 3. So it's a simple square. So the view factor of this surface with respect to this surface will be equal to view factor of this surface equal with respect to this surface. So because it's a square, our dashed surface is a square, we can say f2 prime 3 equals to f1 3. So f2 prime 3 is what is intercepted by these two lines, the radiation emitted by A2 dash and intercepted by A3, and f13 means radiation emitted by 1 and intercepted by A3. They'll be equal. So now using reciprocity, we can say, just using this relation, we get f23 equals A2 prime by A2 multiplied by f13, and we'll use this relation later to find f23, but in this case we don't know f13, so we have to calculate that. Okay, so let's see how we can calculate f13. And f13 is radiation emitted by 1 and intercepted by 3. That's the entire room. Okay, so we also know that f12 is equal to f12 prime. It's similar to the thing that we did in the previous slide. Now to find the value of the view factors, we have to refer to table 13.2, and we'll use the first case that is noted, which is that they've used a rectangular box with two opposite surfaces, and they've given the equation for calculating the view factor for these surfaces. So this matches the description of our problem. We do have our J as our dummy surface 2 prime, and we have I as our surface of the heater. Now we need to calculate these parameters here so that we can calculate the view factor. So our x by L, where x is the width of the plate, which is 1 meter, and L is the distance between the collector and the heat plate in our scenario, which is also capital H and equals to 1 meter. So your x by L is 1 meter. Your y in this case is the uh, depth of the plate, which is given to the length of the plate, which is given to be 10 meters, and the length and L again is the distance between the collector and the heater, which is capital H, and it's 1 meter. So you get your y by L as 10. So after plugging in these values of uh, capital X bar and capital Y bar into this equation, and doing a whole lot of math, we get our view factor for 1 2, which is also equal to view factor of 1 2 prime as 0.39. So now let's apply the summation rule and see if we can find out the other view factors that we have. So our summation rule states that summation or like f11 plus f12 plus f13 equals to 1. We know f11 is 0. We've already established that. So our f13, which is an unknown, can be written as 1 minus f12, which is equal to 0.61. So now we know what is f12, we know what is f13, and we had developed a relation for f23 in terms of f13, which was f23 equals to a2 prime divided by a2. a2 prime was the area of the dashed line, which is equal to the area of the heater plate because it's parallel to it, the imaginary line, so which was 10 meters square, and A2 is the actual area of the collector, the curved surface that is given, and this value is given to us as 15 meters square, and we just found out the view factor for 1 3, which is 0.61, and this gives us f23 equal to 0.41. So, so far we have calculated f12, we've calculated f23, and we have calculated f13, and we know what J3 is, and we know what EB1 is. Okay, so until up till now or up till here, we've seen how we can use table 13.2 and use the dimensions of the collector and the heater plate, or whatever dimensions are given to you for the surfaces, to calculate the view factors. If this would have been a 2D problem, we would have used equations from table 13.1. So make sure you make a note of that, and also note that how using the summation rule and reciprocity and symmetry, we've reduced the number of variables and developed relations to find out the view factors of the unknown view factors. Okay, so now the aim of this problem was not just to find the view factors, but to find the net heat rate to the absorber plate. So for that, we need to calculate Q, and for Q, we will use the resistance approach, or the resistance nodal network approach. So let's say this is the system that's given to us, and we have to develop a circuit diagram for this. And let's make a circuit diagram for this. So whenever you have to make a resistance network or a circuit diagram, whatever you would like to say, for a particular body, you first need to identify how many uh, how many potentials do you have, or how many radiosities you have in the system. So because we have symmetry, we have three different radiosities. One is from surface 1, one is from surface 2, and one is from surface 3. If our surface 3, if we did not have symmetry, we would have four radiosities. If we had a different surface on the left and a different surface on the right. But in this case, because we have symmetry, we have three radiosities. So let's write them down. So this right here, just give me a second. Okay, so this here is J1, or let me just write it here, J1. This is radiosity due to 3, and this is radiosity due to 2. Okay, so you have marked your three radiosities. After you mark your three radiosities, what you do is you um, connect them with the resistance in between. So the resistance between radiosities will always be resistance due to the view factors. Okay, so resistance between 1 and 3, that's 1 and 3, is there's just one resistance. So let me draw that. Okay, then there's one resistance between 2 and 3, and one between 1 and 2. Now what are these resistances? Let's write them down. So between 1 and 3, our view factor between 1 and 3 is F13. So we will write this as 1 A1 F13 inverse. This will be A2 F23 inverse, and this here will be A1 F12 inverse. Oh, okay. So uh, we are on step 2, which is we have defined the view factor resistances between the radiosities. Now we still haven't mentioned the surface radiation resistance. So let's do that. So before we do that, let's note down the emissivities. So the emission by surface 1 will be EB1, which is nothing but sigma T1 to the power 4, by surface 3 it will be EB3, which is sigma T3 to the power 4, and for for surface 2 it will be EB2, which is sigma T2 to the power 4, and the resistance between them will be something that looks like that. Okay, so this was J2 here. Let me move this as well. This is J1. Okay, so our the value of resistance here will be 1 minus epsilon 3 upon A3 epsilon 3. This resistance will be 1 minus epsilon 2 upon A2 epsilon 2, and this here will be 1 minus epsilon 1 upon A1 epsilon 1. Okay, so now we have our nodal network ready, and this is how you make a nodal network. Now what we do is we write or we calculate the currents at each j nodes. Okay, so for example, let's say the current flowing in this direction, and uh, for now I'll say this is Q1 will be equal to current going in. This current will be distributed in two branches. Say this is Q3 and this is Q2. Okay, let's say. So we know that the current moving from 1 is distributed into two parts, Q2 and Q3. Now what is Q1? Q1 is the potential difference between those 2 points, which is sig EB1, which is nothing but sigma T1 to the power 4 minus J1. These are our potentials divided by the thermal resistance, which is 1 minus epsilon 1 divided by epsilon 1 times A1. Now this will be equal to Q2. Okay, so the resistance between these 2 points will be J1 minus J3. This is our potential divided by 1 divided by A1 F12. Right, so that's our Q2 plus Q3 will be J2 or J2 J1 will be J1 minus J2 divided by 1 minus, oh this here will be 3 and not 1, A1 F12. Now we've already seen that this quantity here J3, because there was no thermal resistance, this was just equal to EB3, and we calculated the value for that, and this was simply sigma T3 to the power 4. Okay, so this is at T, this is at J1. So let's do a similar thing at J2. Okay, let's do a similar thing at J2, where you can write the summation of currents, that's the Q's, as, let me use a different color here, maybe an orange. Okay. You can write the summation of currents as sigma T2 to the power 4 minus J2 divided by 1 minus epsilon 2 divided by epsilon 2 A2 equals to J2 minus J1 upon 1 by A1 F1 2 plus J2 minus J3, and now I'll just write J3 as sigma T3 to the power 4 divided by 1 upon A2 F23. Okay, and this is at J2. Okay, so let's see what values do we know here. So at J1 we know the emissivities, we know the areas, we know the surface temperatures, and we know J3. So let's plug in those values and see what equation we get. So say at J1 we will have 56700, which was sigma T1 to the power 4 minus J1 divided by 1 minus 0.9 divided by 0.9 equals to J1 minus J2. We don't know J1 and J2, divided by 1 by 0.39, which was our view factor. And remember that the areas will cancel out because they're equal, plus J1 minus 459, which is the value of J3 that we calculated, divided by 1 by 0.61, and this will give us the equation minus 10 J1 plus 0.39 J2 equals to minus 510582. Okay, so let's say this is equation 1. So in a similar fashion we can substitute values in for the equation at J2 and get the values for that as well. So our equation for J2, after substituting the values, will be, or let's just plug in the values. At J2, our equation will take the form 7348 minus J2. 7348 is sigma T2 to the power 4, which is EB2, into 1 minus epsilon, which is 0.5, divided by 0.5. Areas will cancel out again, equals to J2 minus J1 divided by area is 15 square, 15 meter square, divided by 10 meter square into 0.39. Okay, plus J2 minus 4, so 459, which is J3, 1 divided by 0.41. Okay, so after simplifying this, the equation that we'll get is 0.26 J1 minus 1.67 J2 equals to minus 7536. And the other equation that we had, was minus 10 J1 plus 0.39 J2 equals to minus 510582. So now we have two equations and we have two unknowns. So we can simply solve this for J1 and J2 simultaneously. which will give us J1 uh, equals to, sorry, we know J1, so yeah, so our J2 will be equal to 12487 watt per meter square, and J1 will be 51220 watt per meter square. Okay, now we wanted to find the net heat rate uh, to the absorber plate. So the equation for Q2, the absorber plate was surface 2. So the equation for, let's write it this way. So our Q net will be minus Q going to 2. So we took a negative sign because we had assumed that Q2 was going out of the surface. That's why we have to put a negative sign to find the value of what is going into the surface. Okay, and this will be negative of sigma T2 to the power 4 minus J2 divided by 1 minus epsilon 2 by epsilon 2 A2. Okay, so that's the potential. These two are the potentials: the potential due to emissive power, the potential due to radiosity, and divided by the surface resistance. And this can be written as negative of 7348 minus 12487. We know these values, and these are in watt per meter square, divided by 1 minus 0.5, which is the emissivity, divided by 0.5 emissivity times area, which is 0. No, it's 15 meters square. So it's 15, okay, 15 meters square. Okay, this gives us the Q net equals to minus Q2 equals to 77.1 kilowatt. Okay, so this will be the net heat rate to the absorber plate from the surrounding. So this is how you tackle a problem which involves shape factor and surface radiation resistance and view factor resistances. So make sure you go through this again. You should note how to make the resistance network or the circuit diagram. You should know how to use the tables, information in table 13.1 and 2 to calculate the view factors, and you must use a summation rule and reciprocity rule and symmetry wisely.